Here we are trying to discuss resonance in series LCR circuit. So you need to have a basic idea regarding a series LCR circuit. There are three components used in series LCR circuit: resistor, inductor, and a capacitor in series. The opposition offered by resistor is called resistance. It's pure ohmic resistance. The opposition offered by capacitor is called capacitive reactance, that changes with frequency of the AC source. It is non-ohmic. Even the opposition offered by a inductor XL equal to L omega, that is also varying with frequency, non-ohmic. XC is the capacitive reactance 1 by C omega. XL is the inductive reactance L omega. When all the three components together come in a series circuit, the total opposition is known as impedance, represented by capital letter Z. The expression for impedance is whole root of R square plus XL minus XC the whole square. So we are trying to see how these reactance, resistance and impedance terms change if the frequency of the AC source is increased from 0 to infinity. So the inductive reactance XL equal to L omega, frequency nu, omega is the angular frequency 2 pi nu. Capacitive reactance XC is 1 by C omega. So XL have a direct dependence on omega. XC have an inverse dependence on omega. Now the impedance, the total opposition offered by inductor, capacitor and resistor together is whole root R square plus XL minus XC the whole square. Now the current through the circuit will be total voltage by total opposition. If maximum current, maximum voltage by total opposition. So the maximum current to an LCR circuit series is maximum voltage by the total opposition, which is impedance. Now imagine the first case when omega is 0, frequency 0. Frequency 0 means that's a DC source. So omega 0, XL will be directly 0. XC will be 1 by 0, which is infinity. If out of R, XL and XC, one term is infinity, the addition, subtraction, product, whatever comes, whole term will be infinity. The total opposition will be infinity. Since opposition is infinity, current will be 0 in the circuit. Means in a series LCR circuit, when frequency is 0, it's connected to DC source, no current flows through the circuit. That's given by these values: 0, XL 0, XC infinity, so impedance also infinity, current will be 0. Now imagine you're increasing the frequency from 0. So naturally XL being directly proportional will increase from 0. XC will start decreasing from infinity. So XL increases from 0, XC decreases. So the difference between the two decreases. In the beginning, XL is 0, X is infinity, the difference is maximum. Now XL is increasing from 0, X is decreasing from 0, the difference becomes less. When the difference becomes less, the impedance starts decreasing from infinity. When the impedance starts decreasing from infinity, the current starts increasing. Like that, if the frequency increasing continuously, XL is increasing from 0, XC decreasing from infinity, one particular frequency in this range, you can expect XL to be equal to XC. Only one particular frequency, if we start from 0 till infinity, one particular case, the XL will be equal to XC. When XL and XC are equal, the XL minus XC part will disappear. The total opposition becomes R, resistance. The current maximum becomes just Vm by R. Any other case, if XL is greater than XC, or XL is less than XC, since it's coming whole square, negative part doesn't matter whether XL greater than XC or XC less than XC, there will be a non-zero term. So the impedance will be minimum when XL equal to XC. If XL exceeds XC or XL decreases compared to XC, the Z value, the impedance will be more than R. So this particular case, the impedance will be the least. That particular frequency of source is known as, angular frequency of source is known as omega R, omega resonance. Because that phenomenon is called resonance. When omega equal to omega R, XL equal to L omega R, X equal to 1 by C omega R, both are equal. That time Z will be R. Then current will be just Vm by Z become Vm by R. So this is one particular frequency. Now any frequency less than this, omega less than omega R, omega equal to omega R is XL equal to XC. Then omega less than omega R, XL being proportional to omega R, it will be less than XC. XL is less than XC. So there will be a impedance which have a resistance and reactance term. In this part will not be 0 because XL is less than XC. So the current will be just Vm by Z. This is a case when any value of omega less than omega R. Every case XL will be less than XC. Impedance have this XL minus XC term and current will be Vm by Z. Now imagine a frequency greater than omega R. Now XL equal to XC. Now omega becomes greater than omega R. So XL exceeds XC now. Before omega equal to omega R means omega less than omega R. XL was less than XC. Now it becomes greater than XC. So in that case also it doesn't matter here because the XL minus XC term still will be non-zero. So here impedance is minimum when omega equal to omega R. Omega less than omega R, due to the presence of this particular reactance term, the impedance will be more than R. Even omega greater than omega R, since XL is not equal to XC, this term will be non-zero, so this impedance will be more than R. The impedance is minimum at omega equal to omega R. If it's less than omega R, the impedance is increasing. If the omega becomes greater than omega R also, the impedance is increasing. That's minimum at Z equal to R. That time the current will be maximum. Now if omega is infinity, that time XL becomes infinity, then no doubt impedance also become infinity, current will be 0. So this is the deciding turning factor. Before this all one case, after this all another case. Right? So omega becoming infinity, already we discussed, XL becomes infinity, XC becomes 1 by infinity will be 0. One of the term is infinity, so the impedance also infinity, current will be 0. So if these terms you check, the current was initially 0. Now the impedance is decreasing from infinity, so the current will increase, and here the impedance becomes minimum, which is equal to resistance, the current will be maximum. Beyond that, again impedance start increasing because the reactance term again appear, so the current again start decreasing because impedance is increasing. When omega is infinity, the current will be 0. So this is the variation of inductive reactance, capacitive reactance and impedance, even the current with respect to the variation of frequency of the AC source from 0 to infinity. Now if you summarize this, this already we discussed. Frequency increases from 0, inductive reactance is increasing because proportional to omega, capacitive reactance decreases, the impedance start decreasing from infinity, and the current start increasing from 0. Then this particular case at resonance. That particular frequency, both inductive and capacitive reactance becomes equal, impedance becomes minimum, and the current becomes maximum. That phenomenon is known as resonance, and the frequency at which it happens is called resonant frequency. Now even you increase beyond that, the impedance start increasing, the inductive reactance increases, capacitive reactance decreases. Till the reactance term will be appearing beyond R, so the impedance start increasing and the current start decreasing. Finally, it becomes zero when the frequency approaches infinity. Now this will tell you clear indication how to draw the graph. Start from 0, increases, current increases because impedance decreases and current becomes maximum. Then after that again the impedance increases, current decreases and current becomes 0 at infinity. So this is the graph what shows the variation of current maximum with omega. Even same variation follow with frequency because omega is directly proportional to frequency. Now at resonance the XL part becomes equal to XC. So that's a basic condition for resonance. The inductive reactance has to be equal to capacitive reactance. Now from that we can find at what frequency this will happen. So at resonance XL equal to XC, this is a prime condition for resonance. XL will be equal to L omega R. At same frequency XC will be 1 by C omega R. So you can take omega R both side, L other side. So omega R square equal to 1 by LC or omega R equal to 1 by root of LC. Omega is 2 pi nu, so 2 pi f. So both are fine. So 2 pi fr equal to 1 by root of LC or fr equal to 1 by 2 pi root of LC. So from this is clear, the resonant frequency clearly depends upon only inductive reactance and capacitive reactance. So the condition for resonance is inductive reactance has to be equal to the capacitive reactance, and the factors deciding resonant frequency is only the inductance and capacitance value. There is no role for resistor in deciding the resonant frequency. But at resonance, current is just purely depending upon resistance. There is no role for inductor, capacitor or inductive reactance or capacitive reactance to decide current at resonance. There are two different specific roles. Inductor and capacitor decide at what frequency resonance happens, and at this particular frequency how much current should flow through the circuit, that is purely decided by R. So they have separate roles. Now even you see the graph between impedance and frequency. This is current maximum with frequency 0, increases, decreases 0 again. The impedance starts from infinity, it becomes least R but not 0. The graph will not touch 0, it will be R, then again start increasing and becoming infinity. The graph will be just reverse of this particular. This is the graph for impedance with frequency. The impedance decreases and at resonant frequency become minimum, which is R. Again start increasing, will be infinity when omega approaches infinity. So this is a direct theory topic. You need to learn the factors deciding resonance is L and C, but at resonance current is purely decided by R. And the condition for resonance is inductive reactance has to be equal to the capacitive reactance.